Now that we've got an introduction to forces, motion, and acceleration, we're going to focus in on the 3 laws, according to Isaac Newton, of motion. These are things that we're going to realize are happening all around us all day, every day, and things that we probably recognize, but we want to know scientifically how they're going on. For this first law, we have a few essential questions that focus on the law. This is going to be kind of our key word of the discussion today, inertia. And we want to know, what does an object's inertia depend on? What determines how much inertia an object has, and what happens when this factor increases and what happens when it decreases in terms of inertia. So this will be our focus today as we discuss. We want to focus on that because this law, this first law, according to Isaac Newton, is sometimes called the law of inertia. So what does this law state? Newton's first law states that an object moving at a constant velocity will continue moving at that same constant velocity. And it's important to note that when we're talking about velocity here, we're discussing both speed and direction, so kind of like acceleration. Okay, so with object moving in a certain velocity, it's not only moving at a certain speed, but also in a certain direction. So an object will be moving at a constant velocity. It will keep moving, continue moving at that same velocity until an unbalanced force acts on it. And this is kind of the fancy way of saying this, the scientific way, but really you've heard this before. An object in motion stays in motion, and we know that if we have an object moving, it will keep moving in that same speed and direction until an unbalanced force acts on it. Now, most objects here on Earth, the unbalanced force that changes velocity of something is most likely going to be gravity, right? Gravity, of course, is everywhere, so when I throw a ball, right, gravity starts bringing that ball down to earth. But if we were to erase gravity and I go ahead and throw that ball, it will keep going in that same direction at that same speed, basically infinitely. Now we know we can't really create those conditions here on Earth. A good place to create those conditions or experience the closest to perfect conditions that we can would be in space, right? Space would be without gravity or a very low amount of gravity, a really low amount of friction. We can see those objects move continuously in a perfectly horizontal surface lacking friction infinitely. Right? Here on Earth, if we're rolling an object downhill, we notice that velocity increases due to gravity pulling it downward. Right? We see velocity slowing down of an object being rolled uphill because of friction. Okay? But again, if we were able to construct a perfectly horizontal surface lacking friction, this marble would just continue going on and on and on. Not only does the first law state an object in motion stays in motion, but we also know that an object at rest will stay at rest. If I have an object not moving, like this ball here, used to be sitting on the ground, right, motionless, this object will stay at rest, again, infinitely, unless it's acted on by that unbalanced net force. Okay, here, this person is the unbalanced net force. Their foot applied a force to the ball, sending it off and moving. But if that force did not exist, that ball would just be sitting there at rest forever until that unbalanced force acts on it. So 2 parts to the first Newton's laws. Object in motion stays in motion. Object at rest stays at rest. Both will do those things until they're acted on by an unbalanced outside net force. As mentioned, inertia was a key word for us today because this law is sometimes called the law of inertia. And so, of course, we want to know, well, what the heck is inertia? We've heard it before in the Bill Nye theme song, right? Inertia is the property of matter. So that means all objects, because everything is made of matter, all have inertia. And what inertia is the property an object has to resist a change in motion. Okay, all objects will resist changing motion once they've already been in motion. Like the first law states, an object in motion will stay in motion and it will want to continue that motion until the unbalanced force acts on it. So inertia is just a simple way to state that all objects, because they're made of matter, resist a change in motion. So an object that is moving will continue to move at the same speed and in the same direction, or velocity, right? Continually. This always makes me think of the car example, right? If you're driving down the road 40 miles an hour or so, you hit the car's brakes. Those brakes being connected to the car make the car stop. Right? Brakes equal the car stopping. However, you are not part of the car. You are just the passenger riding in the car. So when the car stops, you, the passenger, continue moving forward because of your inertia. Right? Your resistance to change in motion. Your body has been riding in the car, moving forward at 40 miles an hour. But when the car stops, your body doesn't recognize that and continues to move forward. Of course, that is why we have seat belts in the car, right? To stop you from moving forward and doing what is happening to this guy. So again, objects in motion will stay in motion at that same speed and same direction until that unbalanced force acts on them. The second part of the law, of course, reminds us that if it's at rest, it will stay with a velocity of 0 motionless until that force makes it move. And we see those same motions all the time with amusement rides, right? We have safety bars, safety belts, throughout all these amusement rides because they're going fast and changing direction and speed so often that we need to make sure we keep our inertia handled with those safety constraints. Now all objects do have inertia because, again, inertia is a property of all matter and matter makes up everything. But inertia can increase and decrease just like gravitational force. And it's determined, just like gravitational force, by the mass of an object. Okay, so inertia of an object depends on its mass, how much stuff it's made up of. The more mass an object has, the more it tends to resist that change in motion, meaning the more mass an object has, the greater its inertia is. So kind of a simple question down here. We can see we've got two sumo wrestlers. If I were to apply a force to both sumo wrestlers, an equal force in the same location for each one, it would be much more likely that I would move this sumo wrestler compared to this one, right? Because this guy's inertia is so much larger than the second wrestler over here. The forces will act differently. This guy will resist the change in motion more. So this guy here, more inertia, less inertia, again, due to the mass of those objects. Now I always like to give this personal example of inertia, thinking about the Danny Phantom ride here at the Mall of America. This is one of my favorite rides at the mall, and it's a pretty simple ride. This platform here just continually circles around on this bar. Doesn't go upside down, doesn't twist or turn, but it's one of the more exciting rides, and it has to do with inertia. So let's figure that out. So here I am on the Danny Phantom ride, and it used to be this way. I think it's still the same. It only had a lap bar on it. It didn't have any kind of seat belt. So you, as the rider, just got to sit in the seat. There was a nice amount of space between your knees here and the lap bar, and you just kind of waited for the ride to begin. There's me. Okay. Now what was so cool about this ride is as it circled around, it sped up, going faster and faster, and we know with inertia, a tendency for an object to resist a change in motion. If I didn't have this lap bar on me, what would happen when the platform got to right about here is I would just kind of sail off into the glass ceiling, right? Thankfully, the lap bar is there, but because there was this space between your knees and the lap bar, what you tended to do was fly up off the seat a little bit. Because my inertia resists the change in motion of the platform moving to the left here, I would fly up and slide all the way across, again, kind of like what would happen in the car if you weren't wearing your seatbelt, right? You would keep moving the way that the platform was moving. So you'd lift up and you'd slide over here, and then you'd kind of scoot on back and you'd lift up and slide over here. And it just was a really good time going up and down and back and forth, added to the ride experience more so than just having a seatbelt on your lap. Okay, but I wasn't too old when I started going on this ride, so I always liked to have my dad come with me. And my dad would always say, I don't know why you like this ride so much. And I couldn't really figure it out until I kind of started to understand inertia. Here's my dad. As you can see, my dad's body type is a little different than mine. He has more mass. So for me, as I'm flying around, as the Danny Phantom ride is going up and down, left to right, my inertia is much less than my dad's. Because he has more mass, he also has more inertia, causing him, when the ride goes up and down, to not really move. Right? Because of his higher mass, his body is resisting a change in motion more so than mine. So this flying back and forth, not so much happening for my dad, making the ride less enjoyable for him. But thankfully, he always continued to ride with me anyways. So as we reach the end of our notes here, we still have a little work to do here on the right-hand side. There's some space for you to write a question. Quiz or test question or a question you have about what we've discussed so far with Newton's first law and inertia. And then there's 3 completion sentences. So of course what you want to do here is complete those statements or answer those statements using the notes on the left-hand side. So go ahead and pause, take a second to write out your question you have, either create one or ask one, and then write in your statements. Now, of course, everyone's question is going to be different, but if we look at these completions, we know an object at rest will stay at rest as long as there's no unbalanced force acting on it. So an object at rest will stay at rest. We know because of inertia, an object resists a change in motion, right? That was a key definition that we talked about today, pretty important. And then this third one here, how much force do we need, how many newtons do we need to keep an object in motion? So thinking back to the first law, what do we know about an object in motion? Well, we know an object in motion tends to stay in motion as long as it's not acted on by an unbalanced force. So if we're already moving, how much force do we need to keep it in motion? Well, that is actually nothing. Right? Once that object is in motion, no force is needed to stay in motion. It will continue to move as long as those outside forces aren't acting. Now, on Earth, we know gravity is happening always, nonstop, on every object. So typically, we see that unbalanced force act right away. But just to keep an object moving, no force is needed. So as always, we want to end the notes looking back at our essential questions, answering the summary questions, fill in both what is inertia and what does an object's inertia depend on. What is that factor that determines more or less inertia? And then don't forget on the back, you've got those practice problems about inertia to solve for.